Good afternoon, everyone. I'd like to thank the HPC Advisory Council for having me today, giving me the opportunity to travel to Europe. I'm going to speak about a couple things. The first thing I'm going to talk about is what's the title of the slide, which is New Accelerations for Parallel Programming. The other thing I'm going to talk about after I detail some of these accelerations is a program that we worked on jointly with Hewlett-Packard to actually investigate what these accelerations could do for one-sided communication types of parallel programming languages such as SHMEM and UPC. So I wanted to go into that and give you some results that we were able to obtain from that program. So Mellanox Scalable HPC is a trademark or a name of a fab that are basically accelerators that work with parallel programs. There's a couple of acceleration technologies that we've worked on over the past year or so based on this co-design architecture I'm going to explain. One of those accelerators is called MXM, which is a messaging accelerator. So it accelerates the underlying send, receive, or put, get messages that the parallel program uses. The other is called FCA, which is a fabric collective accelerator, and it's accelerating the collective operations, which are the operations that are used by the compute job that involve all of the processes within the job. The goal with both of these these accelerators is to support a variety of languages. So we're really working with the community to adopt these. There's several MPIs that have adopted them already. For instance, OpenMPI, Platform MPI, IBM's MPI uses it. Intel MPI is testing things right now. The MVAPIC folks have things as well and are doing testing. So we really want the community to pick these up. In addition, besides MPI, we're really looking at alternative languages, such as PGAS languages. So SHMEM and UPC and Chapel and other types of languages, we're working with the community to have those adopt the accelerators. So one of the reasons that we came up with this acceleration technology, or one of the bases behind it, is a co-design strategy that we adopted at Mellanox. And the basis of the co-design strategy is if you look at this picture, you can see that basically we have a network, and that network is being developed by a group of hardware developers, firmware developers, et cetera, and then that network is being used by an application that's running over a communication library. Now these library algorithms typically in the past were developed by software developers that were kind of working independent from the hardware developers. They might have not had a lot of knowledge about the network and about how it worked. They were just algorithms based on a standard networking interface. So one of the things that we saw with this method was that we had this very high-performing network, low latency, high message rate, et cetera. But we would see bottlenecks, and particularly we would see these bottlenecks at large scale. And the bottlenecks were because there were capabilities in the network, features in the network that rise to their full extent by the MPI algorithms. So Mellanox really made the conscious effort to, I would say, move up the stack. So instead of just providing this underlying network, we wanted to bring the capabilities of that network up into the MPI layers and up into these communication libraries. And by the way, it's not really, I would say, tied to MPI. It's applicable to a number of different technologies and different upper layer protocols that are running over the network. So basically, with extending into the MPI, we decided to take a look at the MPIs, work with the developers of the MPIs, and understand how to fully utilize the hardware to its maximum capacity. So the architecture we came up with and the products around it are called ScalableHPC. You'll notice I have these two accelerators, and one thing you can see with this picture is I'm still running over the InfiniBand Verbs API. So we have the InfiniBand Verbs API, which is the interface into the hardware. That all remains the same, but I've kind of pushed up and written some accelerators that sit on top of those verbs. MXM is basically providing reliable messaging optimized for Mellanox HCAs. There's a number of features that it has. It does the connection management. It does the receive side tag matching. It handles all of the transport. And it has a mechanism to actually use the right transport for the right job. So there's a hybrid transport mechanism which allows you to, for instance, use something called UD for when you scale up to very, very, very large jobs. Another really important, I think, feature that we get with MXM is as Mellanox comes out with new technologies, we can put those into MXM, and then if the MPI is using them, it's automatic advantage of it. Instead of us having to go, a good example is a few years ago we came out with a new transport type called Scalable RC. We had to go to all of the various MPIs to be able to adopt Scalable RC, and it can take actually many, many years to adopt a feature like that and get it into the code and into the main stream. So now we can kind of take those new transports. We have a new transport coming out with a new HCA that we're going to announce this week, and we can take that new transport and put it technology down. Like I said, the other acceleration is Fabric Collective Accelerators. There's this technology accelerates the collective operation, and I'm going to show you some of the ways that it does. Basically, it has some optimized algorithms that work over our hardware, such as topology-aware collective algorithms. It takes advantage of hardware multicast that we have in our switch chip to replicate. It has the ability to run over a separate virtual network, so your collective operations don't interfere with any of the other compute messaging or storage traffic. And then it also takes advantage of our core direct hardware offload, which is a hardware engine inside our HCAs that actually offloads the collective operation. So a little bit of background on the different parallel programming models that are supported by FCA and MXM. I think most people are aware of MPI. MPI is a message passing interface. It's based on send-receive semantics, and it also includes the collective operations and collective communication semantics within the libraries. There's some other types of languages. One is SHMEM, or shared memory. It's basically, SHMEM provides a logical shared memory model, even though the processors and the actual physical memory are still distributed. And it also, because I have this logically shared model, I'm able to do puts and gets. So I'm actually able, instead of just having a send-receive like MPI, I have another layer of abstraction where I'm able to do put and get semantics. The last library, or the type of programming language we're supporting today is PGAS, or Partition Global Address Space Languages. This is even a higher level of abstraction from MPI, and it lets you actually operate on vectors across this completely shared memory model, but also have localized global address space as well to for optimal performance for those processors. There's several examples of a PGAS. One is UPC, Unified Parallel C. Another is Chapel, and there's others as well. What we've actually done is we've taken the Berkeley UPC code, and there's an underlying layer that it uses called GasNet. And we've taken that GasNet code and we've integrated our MXM, integrated our FCA into that. And we're getting very good performance results now with UPC. So I want to talk a little bit about Fabric Collective Accelerations, or FCA, and how it works and how we're able to get very good performance and scale with collectives over our hardware. So I think most of you probably know this. A collective operation, though, is basically a operation that is involves all the processes within a job. So for instance, it could be a reduce, which is summing numbers that every process holds. And then the reduce operation will actually add all of those numbers up across the cluster or across the job. They're very synchronous operations typically. By nature, they consume many wait cycles on large clusters as all the processes wait for the job to complete. Some examples are barrier, reduce, Allreduce, all-to-all, broadcast, etc. So collective operations can be a real challenge at scale. One of the reasons is that typically these collective operations are not really topologically aware. So they can be very inefficient when they're using their algorithm, because one process may be talking to a process or another process that's the edge physically of the cluster, where instead it could be talking to a process that's very close to each other. Also, congestion is caused by these collective operations. There's many-to-many communications, so there's lots of messages going around, which if it's not done efficiently can cause congestion and head-of-line blocking issues in the switching fabrics. Lastly, of why collective operations are difficult is that with a collective, you're only as good as your slowest node. So things like OS jitter or having a slow node can really increase variability of your collective operation, and this gets worse as you scale out to very large numbers. Excuse me? Yeah, exactly. So FCA does, or the architecture of FCA to address these issues is we have something called an FCA manager. The FCA manager is topology based, or topology aware. And what I mean by that is that with InfiniBand, we can actually go out and query all of the switches, and we can figure out exactly how the topology looks. So we can figure out if it's a fat tree. For instance, we could figure out here that we had a number of hosts hanging off of a lot of different layer 1 switches. We would know exactly where those hosts reside, which hosts were on which switches, etc. So we can use this information to build a collective algorithm that's very efficient. The FCA manager also sets up a separate virtual network to run these collective operations, and it sets up a IB multicast tree for the results distribution of the collective answer. There's also FCA agents, which are on the compute nodes. It's really not, is a bit of a misnomer. It's really a library that integrates in with the MPI. It communicates with the FCA manager to be able to figure out how it should do the collective. It also has intranode optimizations, and it integrates the hardware core direct functionality into the collective operation. So I want to give a simple example of how FCA would help in doing a collective operation. So I picked a Allreduce operation. I want to show you an example of Allreduce without FCA first. This is a very basic 8 process job. Each of these is process number, and we're going to add them all up. Now, a typical way that someone would do this or write this algorithm is an algorithm called recursive doubling. So with recursive doubling, I pick two pairs and I add the number up, and I work my way down multiple stages until I have my final answer. So my first stage, I have 1 plus 2 is 3, 3 plus 4 is 7, etc. I recursive double again, and I get my answer. Now, this took me three steps to do this, but if you have a large cluster, also when I'm done, I have to distribute my answer to all the other processes, so I send a packet to everybody. So if I have a large cluster, this recursive doubling operation can take quite long. For instance, a 4,000 process Allreduce using recursive doubling would do this kind of recursive doubling operation 12 times, so 12 different stages. Now let's look how FCA can optimize this Allreduce using its topology-aware algorithm. So I've got a little bit bigger job here. I have, 324 host servers, and these are 8-core machines. They're all holding a number 1. So the stages that we're going to do, first FCA knows where all of these ranks are placed within the cluster. So first we're going to optimize and get an answer on every single server. So now I only have one answer on each server to deal with instead of having 8. The next thing that FCA does is it optimizes based on where the servers are within the first stage of the switching fabric. So it's going to basically build a child-parent tree on every switch and get one answer on a single server on every switch. So basically, I add up 36, 18 times. So 17 of those machines send to the one machine. And that happens on every single switch. So the nice thing you'll notice is all the traffic is local. Traffic is going up into the second layer. And if you're doing recursive doubling, you can have all kinds of packets going up there, passing each other. Now I've done my first tier coalescing. Now I'm going to coalesce on my second tier. This is actually the last tier I have to do. I pick a parent again. I'll pick up, and then all the other 18 or 17, I guess, servers will be children. And then I'll send it again. All those 17 will send to the 18th. And then I have my result. So basically 3 stages to do that. Then for the answer, you'll remember in that recursive doubling picture, the answer had to send to every single server a separate packet. As we use multicast. So InfiniBand has hardware replication within the switches. It's something that really doesn't get used very often, and I don't think many MPIs take advantage of it. So what FCA does is it just sends one packet into this switch, and now all of the switches are going to replicate that packet, replicate that result to all the other, however, 2,000 cores or whatever that I have here. So that's how FCA is used in Allreduce. There's other optimizations that FCA does topologically based, depending on what the collective is. Now I wanted to take I have a few minutes I wanted to talk about this collaboration that we've done with Hewlett-Packard to investigate the use of MXM. And this was the presentation was from Zarka Svetanovich, and this was from a webinar that her and myself gave about a month ago on the results of this project. So the goals of this collaboration were to investigate InfiniBand scalability. We were really looking at performance scaling to thousands of nodes. We also wanted to look at memory footprint in those thousands of nodes types of clusters, identify any issues and address them, and really provide a complete solution at the end of it. We focused on one-sided communications, basically PGAS or UPC and SHMEM. So both UPC and SHMEM are very much a one-sided paradigm, so put and get operations for data transfers. The test configuration was a 128 node cluster using HP's SL390s and Mellanox QDR InfiniBand with ConnectX-2. So the workloads that we wanted to look at and what we really wanted to optimize were all-to-all, which are basically all processes communicating at the and also used random puts, so randomly selected nodes and memory locations, and it provided a really high stress on the network. We also wanted to concentrate on short messages, so 8 bytes to 8 kilobytes, and we wanted to concentrate on some other collectives such as barrier and reduce and broadcasts. Okay, so I have a few graphs of some of the results. Basically, this is the all-to-all bandwidth optimizations. We focused on 1 kilobyte to 8 kilobyte messages. Actually, we went all the way down to 8 bytes. This job goes out to, like I said, 128 nodes. I think it's 8-core machine, so we did an all-to-all with all the cores and all the nodes. And you can see here, this is pre-applying our FCA and MXM. The main optimizations with all-to-all are really through MXM, through the messaging. You can see in particular here on the low byte messages, for instance, the 100 or the 1K and the 128 bytes, we get a very good optimization. We get about somewhere around 2 to 6 times optimization, depending on the message size. If I look at that same data and that same test, we wanted to show it as a message rate as well. And you can see the increased message rate we're getting, especially for the low 8-byte and 128-byte messages. So very good optimizations. about up to like 15 times better message rate using MXM. We also looked at memory footprint. This is really the amount of memory needed for communication. It's always a concern when you start scaling up what type of memory footprint you're going to take for the parallel programming jobs. Basically, with MXM, we improved the memory footprint significantly. Actually, about 14 times improvement in incremental memory. Next, we looked at other collective operations such as reduce and barrier. These are barrier results. I think the key to take away from this is these are the number of nodes, and this is the time it takes to finish that barrier. And I have various graphs for the number of PPNs on the thing that's striking is if you look at the barrier results with FCA, it's very flat lined, going from over 100 microseconds to about 14 microseconds. And we've run this, I've run barrier on many more nodes than this, and I see this type of thing going out to hundreds, if not thousands of nodes of this kind of flatlining of the barrier results. Some of the same kind of flatlining with reduce. Basically on 64 nodes, we got a 40x improvement on reduce. And all of these, remember, these were all one-sided communication type programming languages. This was actually SHMEM. So in summary, we saw very good improvements with this project on SHMEM and UPC workloads. We've since productized, Mellanox has productized the SHMEM and the UPC under the ScalableHPC family. They're available on our website as the name Scalable SHMEM and Scalable UPC. They include the package includes the parallel programming library itself that we've designed along with the accelerations. Next steps that we're looking at when you're in the collaboration, we're expanding the investigation to FDR and also their Gen 8. So we look forward to really optimizing further project.